Okay, so I'll tell you about cylindrical coordinates. This you should think as a 3D version of polar coordinates. So maybe we should start with remind me, like revisiting what polar coordinates are supposed to be. Remember that those are coordinates on the xy plane, which are well suited for regions which can be described in terms of like angles or circles. And so the idea is that if you had some point x comma y, right, the polar coordinates, instead of keeping track of the Cartesian coordinates, the distances to the axis, with polar coordinates, you keep track of the distance of this point to the origin, which is r, and you also keep track of the angle between this position vector and the x-axis. And so the change of variables, if you remember it, is that, let's write it here, just by basic trigonometry, because this is a right triangle, you can say that x equals r cosine of theta, y equals r sine of theta. You typically think of r as being positive because it denotes a distance, so you would put here that r is positive. And then for the angle, you only need to go a full rotation to encounter any point on the xy plane. And so you would say that the angle goes from 0 to 2 pi. Once you get to 2 pi, I mean, it's the same as 0, so you can either include it or exclude it in this inequality. Doesn't matter too much. There are other conventions where you go from negative pi to pi. The point is that as long as you have an interval of length 2 pi, you can use that for describing the angle, right? And typically this is like the most useful version. There's a way to go back from polar to Cartesians, which is just saying that r, right, is by Pythagoras theorem x squared plus y squared, or root of that, and then theta is like it's like arctangent of y over x. Although this change of variables will not be, it will be less useful than this change of variables. Now, once you know about polar coordinates, what was one thing you could do with them? Well, you could do integrals, describe integrals using polar coordinates instead of Cartesian coordinates. So maybe this is slightly new, at least from this point of view, but so the idea is that you can also study double integrals using polar coordinates. So let's think about that for a second. Remember that for a double integral, now we have studied functions of, like you want to study the integral of a function of two variables over some region R, okay, where R is not necessarily like a rectangle anymore, because we have considered already more complicated cases. But the point is that you want to study the integral of a function, or compute the integral of a function over some region. And again, here I'm just representing the domain of the function. You have to think that the values of the function in themselves are like lying on a third axis, so that the graph will look like a surface. But it's just better to think about the domain for doing double integrals, because otherwise you don't get much information by trying to do the graph when you try to find the bounds of the function. Okay, so so far what I have told you is that dA is either dy dx or dx dy, right? And that corresponded to either using vertical arrows in the first case, right, for dy dx, or horizontal arrows in the second case for dx dy. And so the point of if you look, these different arrows intersect like in little rectangles, and that's also related to the fact that we're using Cartesian coordinates. Okay, so now what we want to do is something similar, but now from the point of view of polar coordinates. So let's try to describe this element of area. So the point is that this dA, you should think that it represents like a tiny piece of rectangle here. Okay, so let's try to do the same, but from the point of view of polar coordinates. Okay. Moreover, notice that each of these arrows is parallel to the y-axis, and each of these horizontal arrows is parallel to the x-axis. So really, these arrows come from setting one of the coordinates constant. Okay. So now, what are the arrows in polar coordinates? Basically, what you have to do is set one of the coordinates equal to a constant. Okay. So what do I mean by that? Let's go back to this point of view of the polar coordinates. So now we have the xy plane again. But now a point has coordinates, right? If this was a point which had coordinates xy, we're also saying that it has coordinates r theta, where r is the radius and theta is the angle, right? So these arrows, for example, the vertical arrows, are obtained by fixing the value of x, right? For each of these vertical arrows, x is fixed. So let's try to fix r to see what happens. So let's try to fix r. When you fix r, you're looking at all the points whose radial component is the same, right? So that consists of all the points whose distance from the origin is the same, and that's by definition a circle. So what I'm trying to say is that the arrows, or the segments that correspond to having a fixed r, are concentric circles. Okay, so instead of like having vertical arrows, now we have circumferences as our arrows. And the other thing that we can do, right, is fix theta. So what would fixing a value of theta correspond to? Well, theta is the angle with respect to the x-axis. So when you fix theta, you're fixing the inclination with respect to the x-axis. So then basically it's like a ray. So fix theta. right? Each of these rays has a particular value of theta. For example, this could be like 30 degrees, this is like 60 degrees, this is like 100 degrees. So all the points along this ray have a fixed value of the coordinate. So what I'm trying to say here is that, so these are points of fixed value for theta. So what I'm trying to say here is that the arrows in this context are no longer parallel to the x and y axis, but rather they're either rays emanating from the origin or they are like circles. Okay? And so instead of having this little piece of area, which was a rectangle, now you have like a little piece of area, which is this like circular region or circular sector. So let's try to find what the formula for that circular sector should be. So let's try to find this out. So area of circular sector. So let me just isolate a little bit the situation. Zoom in into what's going on here. So okay. So again, the idea is you have two rays which are very, 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 very close to each other. So they're so close to each other that you say that the angle between them is like d theta. That's just to emphasize that remember when you write d of something, you want to think of it as a very small quantity. So here's d theta. Okay? And moreover, maybe this sector is at a distance r from the origin, but then you think that these two circumferences are very, very, very close to each other, so they differ by some distance which we call the r. Okay? And then there's this formula, then the area, like this is not quite a rectangle, this piece, right, because it's a little bit deformed, but the idea is that you can sort of still try to use like a formula of like for the area here being like the length of this segment times the length of this pink segment, just because the difference between these two pink segments is very, very small given our assumptions. More precisely, it's like quadratic in a sense, and then you don't need to, this is like a linearization what we're doing, so you don't need to worry too much about it. And so what I'm trying to say is that the area, the A, should be the length of this pink segment, but well, there's this is like this is a segment of an arc on our circle, right? There's a circle here which I didn't completely finish drawing, but there's a circle there, and there's like a formula for the length of the arc of a circle, which is just the radius of the circle. So this length is the radius of the circle times the length of the angle, which is r d theta, and then the length of this other segment is the r. That one is easier to figure out because basically by default we call that the r. So you see, from this point of view, the actual formula for the area should be r dr d theta. I mean, if you multiply these three things together. So let me write this here. What we just found is that dA, right, for a double integral, dA can be three things. So it could be either dy dx or dx dy, or it could, so those are like the ones that you get if you use Cartesian coordinates. Or it could also be r d theta. And you could also flip these two around in the same way in which we flip the orders here. So you could also say r d theta dr. Although the first one is really the most common, so this is, let me just say this is for polar coordinates, and this one is the one that we will use the most. So let's do an example just to see how this is supposed to work, and then I'll tell you about the story for cylindrical coordinates. It's essentially what we just did, but you just add the z-axis. Okay, so let's do an example here. Let's say that you wanted to find the double integral of this function, x squared plus y squared dA, where R is going to be a region that's well suited for our computations, which is, let's say, it's just a quarter of a disk of radius, say 1, just to make this more easy. So basically, since this is a unit disk, it has equation x squared plus y squared equals 1. So first of all, you realize, well, this is not a rectangular region, so we would still need to do something interesting to compute this. If you use either dy dx or dx dy, you have to write y or as a function of x or x as a function of y, which requires you solving for this equation by taking square roots, which is fine and you can do, but it's not terribly convenient. So instead, what I will do now is the following. So let me do let me write this in polar coordinates, basically because well, the region has some relation to a circle, right? It involves a quarter of a circle, and also the function that I'm giving you, this expression behaves very nicely when you write it in polar coordinates. So typically for problems involving polar coordinates, both the function and the region like interact nicely with the change of variables. So let's see what this looks like in this case. So let's do it. So in polar coordinates, well, first of all, remember that the idea of doing polar coordinates is that every instance of x and y get replaced with their formulas in terms of polar coordinates. So for example, here you would replace x squared with r squared cosine squared and y squared with r squared sine squared. So when you add them together, you get cosine squared plus sine squared, which is 1. And so you just get that this x squared plus y squared becomes r squared. Okay? For the A, if we're going to use polar coordinates, you have to use one of these versions. And again, it happens to be more convenient to just use this one. So I'll just put r dr d theta. Something that I forgot to say is that remember that area dA has units of area, right? So dy dx has units of area because each of these has units of length. Dr d theta has no units because it's like in radians, and it's with dimensionless. So dr times d theta has only units of length. So in order to get something with units of area, you had to multiply by something with units of length, which in this case happens to be the radius. Okay. So here you have something. So sometimes if you forget that you had to add r, you can just use dimensional analysis to figure out that something would be wrong otherwise. So this is a function that we would like to integrate, and the integration will be done just as we were doing the previous integrals. Everything that needs to be figured out is just what happens where with the bound. So again, all these problems about integration always boil down to figuring out the correct bounds. So let me just again think of this as doing the two integrals separately. So first we're going to do the integral with respect to r. Okay, if we're doing the integral with respect to r, well, there's nothing involving theta in any case, but what you would imagine is that you're fixing theta. So remember that this is related to the arrows I just mentioned. Fixing theta was the same as fixing the angle from the x-axis. So if you fix the angle from the x-axis, right, what you're doing here is, let me just draw the region again. We're fixing theta, right? So this has been fixed. And so on this quarter of a circle, notice that this value of r begins at the origin. So r starts at 0, and the value of r ends at the unit circle. So what I'm trying to say is that here, the bounds for r along this ray go from 0 to 1. If you had chosen another ray, right, the bounds for r also go from 0 to 1. So regardless of the ray that you choose, r moves from 0 to 1. And that's why the bound is just two constants and not functions, which is what we were doing a little bit in previous problems. And so once you figure this out, remember that theta is similar to this, what happened in these orders of integration. You can only put constants for the last two bounds, and those have to be the smallest and largest value that the angle takes in this region. And this being a quarter of a circle, the angle has to go from 0, right, to pi over 2. So the bounds are from 0 to pi over 2. Once we did that, then we're good to go. And so this integral now becomes like an ordinary double integral, just with different letters. Probably you did this in Calc 2, but maybe slightly different perspective. But it's the same idea. So this is just r to the 4 over 4 d theta, and this is where r equals 1 and r equals 0, and this gives you a quarter times the integral from 0 to pi over 2 d theta, and that's equal to pi over 8. Okay? So in this case, the double integral just yields pi over 8. Typically, what I have been doing in the previous examples, when we were doing dy dx versus and dx dy, is that I would compute it in with both orders of integration, so that you would see that they give you the same answer. We could also try doing this here, but it's actually there's like an asymmetry between the orders, because really it does matter. It's a lot more complicated to flip the orders. So maybe later we can do an example about that, but at this moment it will be more confusing. Okay, so this is like the perspective of using polar coordinates. Let me just tell you about cylindrical coordinates, and then in the next video I'll do an example with cylindrical coordinates. So for cylindrical coordinates, let's see. Basically what you do is take the polar coordinates on the xy plane and just move them out along the z-axis. So you're not doing anything crazy. You just say, well, you have x, y, z. And again, a point usually would have been specified with Cartesian coordinates. What you're going to do now, imagine this is like the floor, right? You move this floor to this height, okay? So you get a copy of the xy plane. Okay? And then in this copy of the xy plane, you have a copy of the x-axis and a copy of the y-axis. And now you just find the, let me maybe move this point a little bit so that it's easier for me to draw the arrow. And so now what you do is apply the same polar coordinates to this point. So again, you would find the distance from the z-axis. I mean the distance from the origin is really different. It would correspond to this segment from here to here, right? Because the origin is still here. It's 0, 0, 0. When we use this different distance, we'll do spherical coordinates, which I'll do in a couple of videos. But for now, r is now the distance from the z-axis. And then theta is still theta still means the same, is the angle between that segment, same as before. So is it the angle between this purple segment and the x-axis, or the lifted copy of the x-axis. You have to move it first so that it has the correct height. And then if you do this, right, if you just keep track of those two numbers, there will be no way to distinguish between this point and that point, right? They're basically indistinguishable just from the point of view of polar coordinates. What makes them different is that their height is not the same. And so in polar coordinates, what you also keep track of is this distance z. So z is the height of the point. So in this case, the idea of cylindrical coordinates is that of the three Cartesian coordinates, you leave this one, you do nothing to this one, right? So this one remains the same, has the same meaning, and the other two get transformed with the change of variables of polar coordinates as before. So you get this. Okay, and the idea here is that now we're going to do triple integrals, which is something that we have not done before, really, except for an example. And so the idea is that now you still have these arrows that I told you about, right? So some of the arrows, let's try to see if I can do it here. Right, so some of the arrows just corresponds to, again, rays emanating from the origin. The other arrows corresponded to the circumferences, right? And then you also have the arrows. So the rays emanating from the origin corresponds to theta being fixed. The circumferences correspond to the radius being fixed. And then you also have now the third coordinate, which corresponds to the height being fixed, right? And so when the height is being fixed, you get arrows that are parallel to, let's see, well, you can think of this as, in this case, it's like what I want to say is that you have you want, I guess, in the case of cylindrical coordinates, it's not so much that these arrows come from fixing the height. Basically, what you're doing is just, let me explain it a different way. So you have these arrows, and then what you're going to do is move this picture along the z-axis. So basically, you'll do a copy of this here. And then this will look better in the animation I will show you at the end of the video. But let's say that you made a couple of copies. Okay, and what I'm trying to show you is that there's some region, volumetric region in between these two things. Let's say, let's just so that this looks less confusing. Let's say you have something like this. Yeah, now this looks a little bit better. What you should think is that there's some volumetric region between these two pieces of circular sectors, and so this is the dV that we want to compute using cylindrical coordinates. But the point is that dV is obtained by, well, just taking the area of the circular sector, right? So just taking the area of the circular sector that we had before. So this had some area, dA, and multiplying it by dz, okay? And so what I'm trying to, let me just write this with a different color. So basically what I'm trying to say is that before, let me do it here. Before, the volume element in Cartesian coordinates was like dx, dy, dc, or maybe dc, dy, dx, dx, dc, dy, etc. Right? There were like 6 options that we had done if you go back to one of the previous videos. What I'm saying now is that for cylindrical coordinates, the dV is just r d theta times dc. So I'm just saying you take the area from polar coordinates and move it around by some height dc. So that's how you get the volume. And another way in which this is sometimes used conveniently is something like this. And again, usually this is like the most common version. But what I'll do now is, because maybe the calculation of the volume may not be so clear. So what I will do now is show you an animation where you can see how the formula for the volume is obtained. And then in the next video, I'll do an example with cylindrical coordinates so that you see how the volume can be, a triple integral in cylindrical coordinates can be. Okay, so here's a way to think of the formula for the volume element in cylindrical coordinates. So the idea is that to find the volume element, you have to imagine that you increase each of the coordinates by a very tiny amount. So for example, you have the radius in cylindrical coordinates, which corresponds to this segment, and then you increase this radius by a very tiny amount, which is dr, and it corresponds to this pink segment. So so here you start from 0 to r, and then from you add dr, so the total length of the segment is r plus dr. Okay. Likewise, you move from some angle to a new angle by an amount d theta. So this little angle is of size d theta, and so what you have here is that there's a tiny area contained in this region. And what's the area? Well, that's basically the area of a circular sector. So it should be the length of this segment, which I said was dr, times the length of this purple segment or this gray segment. The point being that there's not too much of a difference between these two because everything is being increased by a very tiny amount. So the length of this gray segment is well, r times d theta, because remember that the length of a piece of arc of a circle is always the radius times the angle. Okay, so you find out that the area here is r times dr d theta, which is the formula from polar coordinates, which you probably remember. And then basically in cylindrical coordinates, you just grab this region and move it along the z-axis, so it strips out this volumetric piece, and so the volume of that is just the area downstairs times the height, and the height was again increased by some amount dz. So at the end of the day, the volume in cylindrical coordinates is r dr d theta dc. So let me show you how cylindrical coordinates are supposed to work. Remember that they are basically the polar coordinates that you had studied before, so they're specified by a radius r and an angle theta. But now, in addition to those two coordinates, you introduce a third coordinate, which is the height of a point, and it's essentially the same z coordinate as the usual x, y, z coordinates of the Cartesian system. So it's 2 of polar plus 1 coordinate of the Cartesian system. And so, for example, I'm going to specify this point in space, the point that has these three which is specified by these cylindrical coordinates. So that means that it has a radius of 2.5, but again, this radius of 2.5 refers to the radius of the circle on the xy plane. So basically, imagine that you have this cylinder, that's why it's called cylindrical coordinates, and on the circumference, the outer part of the circle represents all the points of radius 2.5. So here you're increasing the radius from 0 up to 2.5. So you hit here, and then we're going to, so that would be at an angle of theta equals 0. Now what we're going to do is start moving until you reach an angle of theta equals 1.95. And again, this theta is being measured in radians. So let's see. Remember that pi is like 180 degrees, and pi is like 3.14. So this is a little bit more than 90 degrees. Okay, so with these two coordinates, you would have, it's enough to specify a point on the xy plane, and that's how you would typically have done that before. But now in cylindrical coordinates, you can also specify the height of the point. So now we have to increase our height by an amount of 4 because that's the value of c. And so this is the point specified in Cartesian in cylindrical coordinates. And again, you can start moving around any of these coordinates while fixing the other two.